In 1937, deep inside an Oklahoma coal mine, a paleontologist's hammer struck compressed rock from the Carboniferous period. What split open stopped him cold. Pressed into the stone was the fossilized imprint of wings, delicate vein patterns still visible after 300 million years. But these weren't bird wings. They were insect wings. And when the team finally measured the full wingspan, it stretched 75 centimeters, over 2.5 feet from tip to tip. The largest dragonfly alive today maxes out at about 19 centimeters. This ancient specimen was 4 times that size. They named it Meganeura, and the discovery sent shockwaves through the scientific community. Because Meganeura wasn't alone. During the Carboniferous period, roughly 300 million years ago, Earth was crawling with giants. Dragonflies the size of hawks patrolling the skies. Millipedes longer than alligators slithering through the undergrowth. Scorpions as large as house cats ambushing prey in the shadows. For over a century, scientists struggled to explain it. What allowed insects to shatter every size limit we see today? And what force stopped them? The answer revealed something profound about the invisible hand that shapes all life on Earth. Step back 300 million years. The continents are still drifting into place. Pangea is forming, and the planet looks nothing like it does now. There are no flowers, no birds, no mammals, just vast swamps stretching across entire landmasses covered in forests of primitive plants. Giant ferns tower overhead. Club mosses cluster near stagnant water. And everywhere, towering trees called lepidodendron reaching over 30 meters tall, their bark covered in diamond-shaped scars like reptile scales. Walk through this forest and the air sticks to your skin. Thick, heavy. Every breath feels saturated. The ground squelches underfoot, a soup of rotting vegetation and standing water. Visibility is low. The canopy blocks most sunlight, leaving the forest floor in perpetual twilight. And the air hums, not with birds, with insects, wings beating everywhere, from creatures the size of your fingernail to others the size of your arm. But there's something else in the air. Oxygen. Modern Earth's atmosphere contains about 21% oxygen. But during the Carboniferous, oxygen levels spiked to somewhere between 30% and 35%. Recent simulations suggest it may have peaked at 37%. That's a 75% increase over today. And in terms of biology, it changes everything. Insects don't breathe the way we do. They don't have lungs. Instead, they have a network of tubes called tracheae running throughout their bodies. Air flows directly through tiny openings called spiracles, small valves dotting their exoskeleton. Oxygen diffuses passively through these tubes, reaching cells without blood or a pumping heart. Simple, efficient, but limited. The bigger an insect gets, the longer those tubes become. And diffusion rate drops with distance squared. In today's atmosphere, this creates a hard ceiling. Insects can only grow so large before their core tissues suffocate. But in a world with 35% oxygen, that ceiling lifts. Oxygen diffuses faster, reaches deeper. The cost of gas exchange plummets. Giant insects weren't just possible. They were more efficient than smaller ones. Size became an advantage. Size doesn't evolve in a vacuum. It evolves in response to pressure. And in the Carboniferous forests, pressure was everywhere. The forest floor crawled with arthropleura, millipedes the size of crocodiles, some reaching over 2 meters long. These weren't predators. They were herbivores, munching on decaying plant matter and rotting logs. But they were massive, and anything that wanted to eat them needed size to match. Enter Meganeura. With a wingspan stretching 75 centimeters, it wasn't just a dragonfly. It was an apex predator. Its compound eyes contained up to 30,000 individual lenses, each feeding a separate neural pathway. It could track multiple targets simultaneously, calculating distance, speed, and trajectory in real time. Its flight was agile, capable of hovering mid-air, darting sideways, striking from above with precision that would make modern fighter pilots jealous. and its mandibles, reconstructed from fossil specimens, could crush the exoskeletons of smaller insects, possibly even the skulls of early amphibians. But here's what makes Meganeura truly remarkable. Biomechanical analyses reveal something counterintuitive. In modern atmospheric conditions, an insect this size couldn't generate enough lift to stay airborne. The power-to-weight ratio fails. But in a denser, oxygen-rich atmosphere, air resistance increases. And with it lift. The same atmospheric change that allowed insects to grow larger also made flight easier at larger sizes. Meganeura wasn't fighting physics. It was riding them. And it wasn't hunting in isolation. The prey was evolving too. Larger bodies meant more calories, more energy. For a predator, the ability to take down bigger prey was an evolutionary jackpot. This created an arms race. Prey grew to escape. Predators grew to catch them. And in a high-oxygen world, both sides could afford to keep scaling up. But there's another factor. One that's easy to overlook. The sky was empty. No birds. No bats. No pterosaurs. Those wouldn't evolve for another 50 to 150 million years. Insects had the aerial niche entirely to themselves. No competition. No predators hunting them from above. Just open air and endless opportunity. For millions of years, they ruled it. Then the world began to suffocate. Around 250 million years ago, oxygen levels started dropping. Slowly at first. From 35% down to 25%, then 20%, then lower. By the end of the Permian period, atmospheric oxygen hovered around 15% lower than today, and the giants couldn't breathe. But oxygen wasn't the only killer. The Permian Triassic extinction event wiped out roughly 90% of all species on Earth. The lush Carboniferous swamps dried up. Forests collapsed. Massive volcanic eruptions pumped enormous amounts of carbon dioxide into the atmosphere, triggering runaway global warming. Temperatures spiked. Oceans acidified. Entire ecosystems unraveled. Recent fossil analysis shows the decline happened in pulses. Each drop in oxygen corresponded with a measurable decrease in maximum insect body size. The correlation is almost perfect. Size became a death sentence. Smaller insects survived. They always do. Lower metabolic demands. Faster reproduction. The ability to hide in cracks and burrows. The giants couldn't compete. They needed too much oxygen, too much food, too much space. And then came the final blow. Vertebrates evolved flight. Pterosaurs took to the skies. Birds followed. Bats came later. Suddenly, the sky belonged to creatures with lungs. Creatures with active metabolisms. Creatures that could regulate their body temperature. Insects that tried to grow large became slow, visible targets. There was nowhere left to hide. There was another factor too. Fire. In high-oxygen atmospheres, wildfires burn hotter, spread faster. Entire forests could ignite and become unstoppable infernos. Some scientists believe these fires created evolutionary pressure against large body size. Bigger insects couldn't escape. They became fuel. Today, the largest flying insects reach wingspans of about 19 centimeters. The age of giants is over. This isn't just a story about big bugs. It's a story about limits. The invisible boundaries that define what life can become. For insects, those limits were oxygen, physics, and competition. For millions of years, those limits lifted, and evolution responded by pushing insects to sizes that defy imagination. But Earth's atmosphere isn't fixed. It has changed before, dramatically. And when the air changes, everything changes with it. Meganeura will never return. The world that built it is gone, but its fossils remain pressed into ancient stone, proof that for a brief moment in deep time, dragonflies hunted like hawks. And the smallest creatures on Earth grew impossibly large.